Okay, so a number of cells decreases 41% every 8 hours. By what percent does it decrease every 1 hour, 40 minutes, 2 days? So remember that if you're given a percent change and you want a different percent change, the key is that we transfer through growth or decay factors. There's not a fast track from 1% to another. You have to get on the growth or decay factor road. And that's where you can make your transfer between different time frames and then get your percent change. So we've first got to get, we've got the 8-hour decay factor. Sorry, we got the 8-hour percent change. From the 8-hour percent change, we're going to get the 8-hour decay factor. And then from the 8-hour decay factor, we want to get, if we want the percent change every hour, then what do we need from there? 1-hour decay factor. And then from the 1-hour decay factor, we can quickly get the 1-hour percent change. So remember the big illustration that I had, and that you can't go directly from percent change to percent change. You got to get on the decay factor or growth factor. Those transfer directly and quickly. So to get from 1% change to another, that transfer happens across decay factors, not across percent change. Okay, so the 8-hour decay factor, if the cells decreases 0.41% every 8 hours, and the 8-hour decay factor is 0.41, right? Okay, right. So remember with decay, the decay factor is the portion that you keep. When you multiply by some fraction, you're going to keep that amount of the fraction. So you have to make that change. So our 8-hour decay factor is going to be 0.59. So if we have negative 41% change, that's a decay factor of 0.59. Hopefully we've had enough of those that by now that's getting through. And then what's the 1-hour decay factor, right? So this is 1 hour is 1/8 of 8 hours. So every 1 hour you would multiply by 0.59 to the 8th, right? No, this is a partial. This is 1/8 of 8. So you're going to multiply every hour. You would multiply by 0.59 to the 8th, which would result in over 8 hours multiplying by 0.59. And so then you'd get that number, and then anyone got that? 0.936. So then the 1-hour percent change is be the opposite of 1 minus that, right? Again, this is what you keep. We're going to keep 93%, 93.6% every hour. Which means, how much do we lose? 6.4%? And 6.4% is what we lose every hour. No? What did I do wrong? Oh, so it's positive.
Right, which is, I think, the problem that a lot of people have.
Yeah.
Just, you all thought it was supposed to be negative.
Yeah, no, so this is important. So if it's percent change, it's negative. We said this, right, though? Didn't we say this?
Mm-hmm.
If it's percent change, it's negative. If it's percent decrease, then it's positive. So, yeah, I didn't read carefully either. And so, yeah. I know you got it. Read carefully. So, yeah, so it'll be 6.4%. It'll decrease. If it asks for the percent change, negative 6.4%. Okay. Every 40 minutes, we could go back to the 1-hour decay factor. And what would we need to do to the 1 hour decay factor to get the 40-minute decay factor? So for number 2?
1/3.
2/3, right? So 40 minutes is 2/3 of an hour. So you take that 0.936 decay factor per hour to the 2/3 would give you the 40-minute decay factor. And then for part C, 0.936 to the, so 2 days is how many hours? So these would be your decay factors for B and C in order to get the percent change. So from that, you'd have to get percent decrease and percent decrease. Okay, any questions on this example? Okay, so remember, if you want 1% change from another, you make that switch through growth factors. First you get the growth or decay factor for the given percent change that to the growth or decay factor for the percent change that you want, and then from that growth or decay factor, get the percent change that you're asked for. Remember the chart, the illustration that I made on Friday? You have to stay on the road. Stay on the road, which means go between different units by growth and decay factors. Last chance for questions on this one. Okay, so then we were talking about APR and money problems. So remind ourselves that 15, so when you're given an APR, that's a type of percent rate. It's annual, it's yearly, so this annual rate. So A stands for, that's not even on the screen. A annual, okay? So this is a type of annual percent, but it's not the percent change of your money every year, okay? You have to take that number, this sort of quasi-annual rate, and combine it with this thing, compounded monthly, and then work backwards to get what your percent yield is. So the APY is the true percent change per year that you have to figure out. Okay, so the first thing we need to do is get the monthly rate. The monthly rate. So 15% APR compounded monthly, what is the monthly rate? This is the one time when you do get 1%, so to speak, from another directly. It's the one time you do this in the first step of an APR problem. So what's our monthly rate, or how would you find it? Yep, you're just going to take that 15% and divide by 12, right? This breaks the rules for exponential growth, but it's the one time that we do that. It's the one time that we do that. We're going to take that 15% or 0.15 over 12, and we get, we're just going to leave it. Just keep it that way. That's fine. Okay, and so then from the monthly rate, if we have the monthly rate and we want the true annual rate, what do we need first? So we've got, this is like a percent, this is a rate. Now I want the true annual rate. What is my key to making that switch? What is the key to making that switch from one rate to another? I know Nicole knows, I know Daniel knows. What's the key to getting from one rate to another? Yeah, growth factors, right? So I'm going to first get which growth factor? Monthly. From the monthly rate, I can easily get the monthly growth factor. So what do I do to this 0.15 over 12 to get the growth factor? Just add 1, right? It's going to be 1 plus that. There's my monthly growth factor. And my goal is the true annual rate. So I've got the monthly growth factor. From that, I want to find the annual growth factor. Here's where we make the switch from monthly to annual. The growth factor, right? The growth factor is what allows us to do that. And if I've got the monthly growth factor, how do I get the annual growth factor? Yeah, to the 12th, right? To the 12th, because over the course of the year, you will multiply by that monthly growth factor 12 times, right? 1 plus 0.15 divided by 12. Times that, every month, times that, so that over the course of a year, you will have multiplied by that 12 times. So now, if I want to get the APY, here's my annual growth factor. If I wanted to get the APY, what would I do? The true yield. So let's get that number. What is that number? This annual growth factor? 1.16075. Right, a little bit greater than that, right? It's a little bit greater. So 1 point, what'd you say? 1.16075. Therefore, what's the APY? What's your true percent increase per year? 16.075% would be the true change, percent change per year. If it was 15% APR compounded monthly, the percent change is truly 16.075%. Okay, but this question says, how much will 10,000 be worth after 7 years? So if I want to know what it's going to be worth after 7 years, then I want to get another growth factor. Which growth factor do I want? I've got the annual growth factor. So now with the 7-year growth factor, which would be our annual growth factor it's got the annual growth factor, and what do I want to do with it? Over 7 years, you will have multiplied by the annual growth factor 7 times. So we're going to just take that annual growth factor and keep multiplying it together 7 times, and that's our 7-year growth factor. So then what's the amount after 7 years? Here we've got the 7-year multiplier. So we start with $10,000, and we've got the 7-year growth factor. How much will it be worth after 7 years? What do you do? What is a 7-year growth factor? It's a multiplier on output to get the output 7 years later. It's a multiplier on output to get the output 7 years later. Therefore, 10,000 times that. That's right. It's going to be the multiplier on an amount to get the amount that much time later. So we do 10,000 times so how much? This would be a nice chunk of cash here. 50, 60,000, what is it? 28,000? Nice enough. 390. 1. I'm not sitting right next to you. I have great hearing, but I'm not sitting next to you, so you can't talk in normal voice. 2, 28, 391, 13. Did I get it right?
Yeah.
Okay, so what if we were doing see, it's monthly. So, okay, so let's look at monthly. That later. Okay, so let's go back and look at this situation again. If we had, say, R was your APR, and you were going to compound n times per year. So now R so that's the decimal version. R is the APR, that's decimal. Okay, and we're going to compound n times per year. So we're going to go through this process again, but looking at just if it's generically, if R was the APR, and we're going to compound n times per year. So the first thing you're going to get is your period rate. Per period rate. Just like up here, we got the monthly rate first, right? So now just per period rate will be what? Yeah, you're going to start, again, this first, you've got APR, and you're going to compound n times per year. The per period rate will be R over n. That's what this is doing right here. But now we're just generically any rate and any number of compoundings per year. And then the next thing we need is the period growth factor. So if the period rate is R over n, then the period growth factor is 1 plus R over n. And now I want the annual growth factor. So we're compounding n times in a year. So we'll take the per period growth factor and raise it to, we'll multiply together n times. If we're doing it n times in a year, we'll multiply that period growth factor together n times to get the annual growth factor. Okay, and then what would the t year growth factor? So any number of years. So this is annually what you multiply by, then what would you multiply it by every t years? The annual growth factor to the t. Over t years, you would multiply by that annual growth factor t times. So then an initial amount P is worth how much after t years? So if I have an initial amount P, and I've got the t-year growth factor, what do I do to get how much that amount will be after t years? You're going to take your starting output, multiply by the t-year growth factor to get the final output. So it's going to be P times 1 plus R to the n, to the n, to the t. And we call that final amount A. And it's a function of how many years goes by. And so this some of you may have seen this before, but I would bet you haven't seen it in this way, that it's all about growth factors. Do you see this? 1 plus r over n, what is the meaning of that? What is 1 plus r over n? That is the period growth factor. So if whether that's 1 month or 1 quarter or 1 day, it's whatever period we're compounding, that's the growth factor, the multiplier for that period. Okay? And then we have that thing to the end. What's that? So you multiply that together n times, you get another growth factor. That's the annual growth factor. And then if you multiply that together t times, you get another growth factor, the t-year growth factor. Okay? So this compound interest formula, where many of you may have seen this before, now you understand what it means. It's all about growth factors. There's 3 of them in there. And then we know if you have an initial amount and you want to know what's worth 2 years later, that's what a growth factor is. It's the multiplier on an output to get the future output. In this case, t years later, the output t years later. Okay, questions on that? So really important that you can identify where this formula comes from and all the parts and pieces, what they mean. Okay, so let's look at what happens when you compound more often. So we had monthly here. So let's write down here. So let's look at monthly, and then let's look at daily. So in this example back here, our monthly growth factor was 1 plus 0.15 over 12 to the 12th. And that was an APY of okay, what APY did we get for monthly compounding? Yeah, we got so that was 1.1608, and so that's a 16.08%. Is that right? Is that what we got? Okay, so the APY, so for this 15% APR compounded monthly, truly results in a percent increase of 16.08% over the year. So now I want you to find the daily growth factor, and then the annual growth factor for daily compounding, and then the APY. Okay, so for daily, what would the daily growth factor be? What would the annual growth factor be? And what would the APY be? So that all starts with the daily rate. What is the daily rate? As an expression, right? So just how would you find the daily rate? Yeah. Yeah, so you would take your APR, and now we're compounding daily, so your daily rate would be 0.15 over. That's your daily rate. Okay? And then the daily growth factor from that? Plus 1. 1 plus that. That gives you your daily growth factor. And now how are we going to get the annual growth factor for daily compounding? You're going to multiply. So every day you would multiply your amount by this. So over the course of a year, you will have multiplied by that thing 365 times. And you're going to get the growth factor. And after you get the growth factor, and you should get then a percent increase of, did you get 0.18? You should have gotten that daily growth factor to be 1.1618, which is percent increase of 16.18%. Okay, so here's the moral of the story. As we compound more often, we get a higher APY, but it just doesn't go off like indefinitely. Like the percent just doesn't go to infinity. It levels off, right? So it's getting greater, but it's slowing down and leveling off. So what's the most that we could compound? So here's compounding monthly 12 times a year, compounding daily 365 times a year. So then we could compound hourly, we could compound every minute, we could compound every second. And then if you continue that line of thinking, you keep cutting times into smaller and smaller time increments and taking more and more of them, there's this idea of compounding continuously, every moment. That says continuously. So it's kind of like 1 plus 0.15 divided by what? Infinity. And taking that to the infinity. So figuring out what that is requires some more advanced mathematics that we don't want to take the time for, okay? But I'm just going to, and I would love to have that conversation if you wanted to in office hours. I'm just going to erase here. So some room. So this is the idea of continuous compounding. And so this formula down here changes. You can't plug infinity in for n in this compound interest formula. So when you do the math, the math that gives you the equivalent formula for, we think of n being infinity, you get a different formula. And let's write that down if I can erase here. Okay, so this is the idea of continuous compounding every moment. And we get a new formula because we can't plug infinity in for n, but there's some math we can do to get the equivalent formula for this idea of compounding every single moment. And this is what it is. It's P. So our initial amount, and then our growth factor would be E to the RT. R is still the APR. T is still the number of years. And then this E is a number like pi. It's a constant number, a non-repeating infinite decimal like pi. So it's 2.1.828.1.8.2.8.4.5. And then that keeps going on. Numbers go on and on and on and on for infinity. Okay, so it's a number similar to pi, the way the behavior of it, right? So it's like it keeps going on and on, it doesn't repeat. And it's this number that it's what's called the natural base. The natural base. It's this number that relates to compounding continuously. It's the base that you get that relates to compounding continuously. Okay, so let's see. So this is what? The e to the RT is the t-year growth factor then for so let's find it. So you're going to take e to the, what's r? Still r 0.15. And then in this thing it was 7 years. And then times 10,000. So let's get the final amount. And this will be our A of 7. So 10,000 e to the 0.15 times 7. Anybody got it? I've got it here. It should be 28. If you do that, you should get, and everyone do that, so make sure you're putting this in your calculator right. You should get 28,576 and 51 cents. So look, we're raising, this is the t-year growth factor, so then what is the 1-year growth factor? Can you see it in there? So what are we raising to the t? That's our 1-year growth factor. E to the r, see that? So e to the r then is the 1-year growth factor. Raised to the t power gives the t-year growth factor. So I just want you to go back here and find e to the r. So e to the 0.15. This is going to be the 1-year growth factor. And you should get 1.1618. Keep going.
1618342.
So let's do 3, 4. So look, so continuously, compounding continuously means what percent increase? What percent increase? If it's 15% APR, what percent increase is it? 16.81834%. That's the best you're going to do with 15% APR. You can't compound any more than every moment continuously. Okay? So we see that the APY, the more you compound, the higher it gets, but then it levels off, and the maximum amount you can have for an APY then is what you get when you compound continuously every moment. You can't do any better than that. And so 15%, the most it could be worth is if you compound continuously, and it would be worth 16.1834%, not any more than that. Okay, so we have the compound interest formula for finite compounding, so at n times per year is this one. And then for continuous compounding, we can't plug infinity into that, so it switches to this. But you still can see the growth factors. Look, e to the r is your annual growth factor, and then that thing to the t is the t-year growth factor, which you multiply by p to get the amount after t years. Okay, so what happens is this now, if we return back to just any exponential growth, gives us another way to look at all these exponential growth problems we've been looking at. This gives us an alternate kind of view of it through this value, which we call the continuous rate. This is like the continuous rate, so APR. The continuous rate, what? It's not the true percent increase or decrease because it's like APR. You have to combine it with continuous compounding to figure out what the true percent increase is. So let's look at that. Any questions on the money stuff? So now we're going to return back to just any exponential growth and now we have this alternate way of looking at it. This alternate way of viewing exponential growth through the eyes of what's called the continuous rate, this R value. So let's do that. Can I erase? Here we go. Okay, so this is what we said. We said continuous compounding was PE to the RT. Remember, the continuous rate R is not the true percent change. R is like APR. Only when it's combined with continuous compounding is the actual percent change known, like the APY. Okay, so recall our general exponential growth formula. What was it? So how did we model all exponential growth as a function formula before? Said no. Yeah. You're about to say it. Yeah. Yeah, that's it. A, B to the X, right? That should be familiar. A is called the, what is A? Initial value. And then B is the centerpiece. What is it? Growth factor. It's what you multiply by every output to get the next output, right? So now we can write this in an equivalent form. We can write this as A times E to the KX. Okay, which we're pulling this from this continuous compounding idea, PE to the RT. But we're going to write it now, AB to the X is AE to the KX. So now we have two ways of looking at any exponential growth. Okay, K is the continuous rate. K is the continuous, it's called the continuous rate. But here's the thing that's tricky, that really throws students off. It's not how much the quantity increases per unit. Why? That K is like an APR, right? APR, which is not the true percent increase. So let's compare these two forms. A is A, right? The initial amount still is the initial amount. A is A. The input is still the input. Okay, so then what is the growth factor B equal to? E to the K. So B equals E to the K. So B, what was that? That was our growth factor, right? Did that growth factor represent? Did it reflect true percent change or not? B, does it reflect the true percent change per unit? If B was 1.14, is that reflecting? Is that showing the true percent change? How? What is it? 14%. 14%. That's the true percent increase. So B reflects the true percent increase. So B is the true growth factor for 1 unit of X. It reveals the true rate of increase. So B is the one that reveals the true rate of increase. What we've been doing the last 2 weeks. Given a B, what's the percent change? Given a percent change, what's B? Now we've got this new thing, this weird thing that's like APR. That's K. It doesn't reflect the true percent increase, but it is a type of rate, and it relates to 1 unit. But it's not the 1 unit percent increase. It's weird. It's like APR. Okay, so all that stuff is still there up there at the top. Okay, so suppose a nation's population has a 1-decade continuous rate of 19.2%. So, this is the 1 decade continuous rate. Does the nation's population increase 19.2% every decade? Yes or no? Does it increase 19.2% every decade? No, because it's a continuous rate. If it says it's a continuous rate, it's like APR. It's not the true percent increase. So this continuous rate of 19.2%, what does it have to do with all this stuff up here? What symbol do we have that relates to 19.2%? K. K equals what? No, K is the continuous rate as a decimal. Yeah, so here's the thing with this B equals e to the K. B is a growth factor. K is a rate. So B is our growth factor. It's a multiplier. K is a rate. It's just not the true rate. So here they're giving us that number, and it's 0.192. So we've got K. How are we going to get something that will give us the true rate? How can we get something that will give us the true rate? If K is 0.192 and we want to figure out what the true percent increase per decade is and then per year, what's the key? Yeah. Nope. So did you say? Yeah, maybe something like that would work. But what did someone else say? Yeah, get this, right? If you can get B, B is the same B we've been using the last 2 weeks. From that B, we can get the true percent change. So B equals e to the K. Anyone got it? 2117. How about that? Okay, so now that's the true growth factor per decade. True decade growth factor. Therefore, what's the true percent increase per decade? 21.17. So a continuous rate of 19.2% means a true percent increase of 21.17%. That should feel like the whole APR thing, right? When this thing is compounded moment by moment on top of itself, then over the course of 1 unit, you truly get a percent increase of 21.17%. So this thing is the key right here. But you've got to know what things mean. K is the continuous rate. B is your true actual growth factor. Now we've got the percent increase per decade, and we divide by 10 to get the percent increase per year, right? No, percent increase is not directly transferable. What's gonna be the key to getting from decades to years? You're gonna get the 1 year growth factor. So you've got the decade growth factor, find the 1 year growth factor, and that gets you the 1 year percent increase. Do it. To get the 1 decade growth factor, or the 1 year growth factor, we raise it to the 1/10, and we got 1 point what? 0.194, which means 1.94% increase per year. So now we can write the population function, so let's call it f of t. We can write that in 2 ways, old way and the new way. So we can write it old way and also the new way. 2 different forms of the exact same function. So do it. So write if we want a function that outputs the population t decades after it had a population of 230,168. So can you write that in 2 ways? So old way would be times what? It's going to be times the 1 decade growth factor, 1.2117, to the t. That's the old way, right? Initial amount, 1 decade growth factor, to the number of decades. New way would be e to the k as a decimal. 0.192. So remember, k is a rate. It's like a percentage. It's not the true percentage increase, but it's the type of number it is a percent or a rate. Okay? And then that to the t. So these are the exact same function. If we were to graph that one on the left and graph that one on the right, it'd be the same set of points, same curve, same set of points, just a different perspective on it. The growth factor versus what we call the continuous rate, which is not the true rate of increase per unit. Okay, so for Wednesday, what do we got? Swab work. Swab work for Wednesday.
What do you want us to do with our written work?
We need to hand in the homework. So can you pass it? If you can do that a minute before class, just go ahead and.
Everyone is here. This is why.
It's okay. Then we need to get it turned in. It's okay. Just go ahead and hand it to either myself or LP on your way out.
So hey, Mark.
Hi.
Sorry for being late, but you wanted to talk to me about the whole absences thing?
But you wanted to talk to me about the whole
Oh
absence
yeah, yeah.
thing.
Sorry.
Right.